Welcome to the Alpha Training and Consulting's online training program. Today's module is entitled, What is Measurement Uncertainty? So that'll be a good question to have an answer to, but remember, we've been preparing students for ASQ certifications for over 20 years. We've become very good at it, and we'd love to have you as one of our students. But back to the question, what is measurement uncertainty? The term measurement uncertainty is used internationally to describe the quality of a given measurement. The gauge R&R, that was studied in an earlier module, as you'll recall, is a form of an uncertainty study. If you found the only variability in a measurement system was repeatability, sigma of the equipment, and reproducibility, sigma of operator to operator, if those were the only two elements of a measurement variation, then the gauge R&R study may be an acceptable uncertainty study. So an uncertainty study is nothing more than calculating the standard deviation of the measurement system. What differentiates it between gauge R&R and uncertainty? Uncertainty doesn't stop at just repeatability and reproducibility, as you'll see here in a little bit. It's a much deeper dive into measurement standard deviation. Most experts agree that if an uncertainty study is to be looked upon as a credible study, it should, as a minimum, consider repeatability, sigma of the measuring equipment, reproducibility, sigma of operator to operator, variation due to the reference standard, variation due to resolution, measurement resolution, temperature, humidity. You should have at least those if you're going to do an uncertainty study, and you may have much more than these, but this is just the basis. Remember, gauge R&R only considered those two elements. We're going to consider many more elements. It's a much more in-depth study of measurement standard deviation. Like the gauge R&R study, the uncertainty analysis is nothing more than a standard deviation calculation, standard deviation of the measurement. All right. As an example, let's say we wanted to calculate the combined or total standard deviation of the assembly below. So we have these stacking blocks, part 1, part 2, part 3, part 4, and these are coming down the production line all the time, and we measure the whole stack. We want to know, if we know this standard deviation, this one, and this one, and this one, can we add them together? The answer is yes. We've discussed this earlier, but I'm just going to go over it again in a little better detail. So this is how we'd add them together. Standard deviation, or sigma of part 1 squared, sigma of part 2 squared, there we go, sigma of part 3 squared, plus sigma of part 4 squared. Add them all their squares together, take the square root, and that will be the combined standard deviation. So now I put numbers in there for the standard deviation of each block. And notice I'm going to add these together now. 0.05 squared, 0.033 squared, 0.09 squared, and you can't see it, but this is 2000 squared. That's how you add them all together. So I square all those, as you see, add them together, take the square root of that. That gives me my combined standard deviation. Well, that's what an uncertainty study is. We have repeatability, reproducibility, change in temperature, change in humidity, etc., etc. You put all these in there, square them, add them together, take the square root, and that will give you your uncertainty value. Okay, so there we go, and we call that, we could call it combined standard deviation, but in measurement we call it combined uncertainty. And that's how you add those sigmas together. One of the difficulties of calculating uncertainties is there are 4 different traditional formulas that are used to calculate uncertainty or standard deviation. These 4 formulas with their corresponding distributions are shown here. So here is the standard deviation of the normal distribution. That's the formula. If you have a rectangular distribution, also called a uniform distribution. And what does that mean? It means the odds of getting any given number are all equal. We used an example when we talked about distributions of people lining up according to their height. We had 2-foot tall line, 8-foot tall line, and of course the middle would be 5. And you have equal numbers of all those heights of people. Usually it looks normal, doesn't it? But sometimes it's a rectangular one. And sometimes in measurement, the phenomenon is represented by the uniform or rectangular distribution. Well, here's the standard deviation formula for that. This, as you'll find later, is called a type B calculation. This is a type A calculation, because this is just going off the tolerances. It's saying, okay, it should be this long to this long. That's the whole spread, minus A plus A. So you take the distance from the average to that outer edge, that's A, divided by the square root of 3. It's a very easy calculation, right? And here's the triangular distribution. It's a little bit like the normal, isn't it? You're more likely to find the true value right in the middle, but the probability goes down linear in this case as we go away from the average. And A is just that distance from the average to the upper spec limit, if you will. And you take that distance, A divided by the square root of 6. That's how you get the standard deviation for the triangular distribution. Notice the probability is higher at getting values near the outside edges on this distribution. Okay, and this one is A again. I didn't write that down, but this is plus A minus A. The distance from the average to the outside upper spec limit, for example, that would be A. A divided by the square root of 2. So these are the various formulas. Notice these formulas. A is a spec limit. So this is calculated from a spec limit. Very easy calculation from a spec limit from a spec limit. They call these type B calculations. But if you go out, collect data, crunch the numbers, kind of experimental type stuff, that's a type A measurement. The gauge R&R study is a type A measurement because we have to go out there, have 3 operators. Each operator measures each part 10 times. And then we calculate all the different various standard deviations, etc. And so it is real data crunching, collecting, experimenting, collecting data type thing. So that will be type A calculation. You want some type A calculations. You don't want them to be all type B. These are kind of canned and not as accurate as if you go out and really run an experiment, validate the shape of the distribution, etc. So they're not as rigorous. Type B calculations aren't. So when you finish on your uncertainty, you want some type A's in there also. Gives it more credibility. Now, I'm not going to go over every one of these, okay? I do that for the students preparing for a certification exam, but we're not going to do that here. But I will go through one. I'll go through the triangular distribution. The triangular distribution is shown here. Its height is 1 over A. A is a spec limit, again, plus minus. And that's what it looks like. Where we're most likely to find the true value, right in the middle, then the probability decreases as we move away from it. That's the nature of the thing. The triangular distribution is most commonly used for situations where the probability of an outcome is most likely at the center of the variation range, as I already mentioned. The range is usually defined as a specification or variation limit. The A's there, plus A minus A. Okay. So for example, let's say A is 2. And minus A is minus 2. There we go. If, for example, if I have a specification or variation limit of plus minus 2 millimeters from the target value, then plus A will be equal to 2, and negative A will be equal to minus 2 millimeters. The formula used for calculating uncertainty or standard deviation using the triangular distribution under the assumption of the triangular distribution is shown here. Like we mentioned earlier, it's A divided by the square root of 6. There it is. I just took it from there, put it on this slide. The most common use of the triangular distribution in the uncertainty analysis includes when the only data available is variation limits and the highest probability of the outcome of an even event lies in the middle and less likely near the edges. That's when you use this formula. Temperature between 2 standards is an example of such a variation. Okay, so we'll use that as an example. For example, let's say the temperature between 2 standards is most likely 0, but could be as high as plus minus 2 degrees Fahrenheit. One very important thing that the technician should remember in an uncertainty analysis is that every standard deviation or uncertainty must use like units. In other words, if the other uncertainties were in units of inches length, then in our example, we must convert the plus minus 2 degrees into plus minus inches. Well, how do you do that? So we must determine how the range of plus minus 2 degrees Fahrenheit impact the length in inches of the standard. To do this, we use this formula, coefficient of expansion times the original length times change in temperature. And if it's steel, the coefficient for steel, which we'll use right here, is 11 times 10 to the negative 6th. Original length, we will assume the standard to be 6 inches long. Current length then, we multiply 0.011 coefficient of expansion for steel, times the 6-inch length, original length, times the change in degrees Fahrenheit, which was 2 degrees, and that is our value in inches. Okay, now we take this 0.000132, put it in the numerator. Remember, we're just using this formula back here, a divided by 6. A is that expansion. Divided by the square root of 6 gives us 0.40, it looks like there, 539 inches would be the standard deviation. There's some other expansion variables, and you can look those up many different places. Because the uncertainty due to temperature change was calculated using variation limits, specification limits, instead of data collection and statistical analysis techniques, we consider this to be a type B evaluation technique. Traditionally, when you use the triangular distribution assumption, you use the type B evaluation technique. Now, this is oftentimes all the things that are considered in an uncertainty study. The national standard, this is the calibration standard, master standard, working standard. You take into account all those. But what you must know, when you buy this instrument calibration, which will probably go in your calibration lab, it will tell you the uncertainty right on it. So you don't even have to calculate it. It's already in the owner's manual. And just so you know, in almost every case I've ever seen anyway, when you get that standard and it gives you the uncertainty value, it adds all these uncertainties together. So you don't have to go back and find out what all these were. Someone already calculated it for you. So when you get this, you'll see uncertainty equals, it'll actually say K2 equals, 2 times K equals, that means 2 times the uncertainty or 2 times the standard deviation. All you have to do is divide that by 2 and you'll get your uncertainty for that. And you'll have that whole lane taken care of. Then, of course, instrument, sigma of instrument takes place during the gauge R&R study. That's the repeatability value. And so that's the measurement system right there. Then you have the measurement process, which includes the operator. We do that in gauge R&R, as you'll recall. That's the reproducibility. So we have that, and usually the procedure and that's all combined into this. Okay, and you combine operator to operator and instrument, you get sigma of the measurement there. Data analysis, display of interpretation, we take that into account also, the resolution. And then the fixturing and connections, the test environment, change in temperature, change in humidity, etc. And we take all these things into account for our uncertainty study. All right, now that you have the value of uncertainty, let me show you how they use that. Okay, so let's go to the whiteboard and discuss that in greater detail. All right, here we are at the whiteboard. Let me explain what they do with uncertainty. They have this thing called the K value. The K value is like Z. It's the number of sigmas. K is the number of sigmas. K equals number of standard deviations. So that's one thing you have to remember. And usually when you buy an instrument, they'll calculate sigma for you already of the instrument, repeatability, for example, or of the standard, whatever the case may be. But it will say 2 times K equals, and it will give you 2 times the uncertainty value. Okay, just so you know. So it's easy, right? If you want to know uncertainty, you just divide it by 2. But there's a reason they do 2 times the uncertainty, because 2 times the uncertainty plus minus 2 uncertainties, or 2 sigmas, represent 95.44% of the data points, if you'll recall. Plus minus 2 sigmas, 95.44, and they give that confidence interval. They don't call it 95.44. They just go out plus minus 2K, or 2 standard deviations, plus 2K, minus 2K. And this is called, okay, they have a name for this expanded uncertainty. It's really a confidence interval, but they call it expanded uncertainty. Okay, there you go. So you take the 2K, take it from the measured value, go 2 sigmas out, go 2 sigmas below. That's called the expanded uncertainty. What does that mean? Expanded uncertainty says that there's a 95% chance. Okay, 95.44, but we just round it to 95%. Keep things simple. 95% chance that the actual true value, I know you measured it as this, but that doesn't mean it's the true value because there's uncertainty involved, sigma measurement. And so they're just saying, hey, there's a 95% chance that it will lie between the upper expansion and lower level of the expansion. Okay? 95% chance that the true value will lie between those values. That's what the expanded uncertainty does. Now, how do we use that? Well, that's a good question. Remember, in gauge R&R studies, we were plus minus 30%. Percent gauge R&R had to be 30% or less for it to be functional. We don't have those rules with uncertainty. What we do with uncertainty studies usually is you have an upper spec limit. This is on a part, by the way, and a lower spec limit. You define what a good and bad part is by the spec limits. Then you measure a part. Okay, and the measurement is right here, but you have to show, this is in real critical situations. Maybe you're shipping up a multi-billion-dollar satellite and you want to make sure everything's right. So you measure this point. Then they subtract 2K from it, add 2K to it, and the whole expanded uncertainty lies within the spec limits. So it's a good part because there's a 95% chance that it's within the spec limits, even higher. Okay, so that's not bad. Now, what if you do this? You measure, and it's outside the spec limit, so it's not looking good. So you measure here, add your 2K there, subtract your 2K, you have your expanded uncertainty. There's a 95% chance the true value lies in between those two values. This is a bad part, no doubt about it. So that's not bad. But this is the difficult situation. You measure. Oh, it just barely made the spec limit. Subtract 2K, add 2K, and you straddled. You don't know if it's a good part or a bad part. Because the true value, 95% of the time, will lie between here. Part of that lies outside the spec limit. This is called, that means you need to make a decision. So there's these standards. I'll show you later exactly what the standard is. But they have rules for making a decision on whether it's a good part or a bad part. And I'm sure part of it, you just keep measuring that same part over and over again. And the Central Limit Theorem says that draws in these limits until you get to the point that it's on one side or the other, so you know if it's a good part or bad part. But there's standards. There's many ways you can determine where the true value is. And you'll have to reduce, of course, the standard deviation to figure that out. But that's how you use the expanded uncertainty. And you do it in critical situations. Aerospace, I imagine, uses that once in a while. Automotive usually uses gauge R&R. People shipping up satellites, I'm sure they use uncertainties. All right, back to the PowerPoint. I think we've covered this pretty well. All right, here we are at the uncertainty budget. So this kind of the end game is where you put everything together. This is the reference standard, magnitude 5 thousandths, which means the standard uncertainty is 0.0025 because that is 2K there. Okay, divisor 2. Where did the divisor come from? The square root of 2, remember? So you put those things down. And the standard uncertainty then is 0.0025. And if you square it, why do I square it? Because I'm going to add all these together and then take the square root to get my overall uncertainty. Anyway, the uncertainty budget also says this is a type B calculation, type B calculation, type A calculation assumes a normal distribution, type A that includes the rectangular distribution. So I have a couple type A's, a few type B's. That's always a good combination. And then any comments, where did I get my A value from the calibration certificate? Where do I get my A value from for this rectangular distribution or resolution? From the owner's manual of the manufacturer. And where did I get this? From the gauge R&R study. See thermal expansion sheet for my triangular one. That's the one we went through. And the C calibration procedure, etc. Then you should pack this thing with comments. I didn't put that much here. But auditors like to see comments. Professional auditors that audit these studies like to see all the assumptions you made, etc., etc. I put one note. Humidity is considered a non-issue as it is controlled within a range of 20 to 35%. So those things that you leave out, you should at least put the reasoning for why you left them out, for example. And this is, again, the uncertainty budget. Now that you have that, you multiply it by 2. That gives you your 2K. And then whatever you measure, you add and subtract that from that measurement value to see if it straddles the spec limits. If it doesn't, then you know it's good or bad, etc., as explained earlier. So uncertainty budget is pretty thorough. Okay, you have to dig pretty deep. And if you do one, the hardest one is your first one, I can tell you that. But after that, they're pretty easy. They're not anything you need to be concerned with. They're not that difficult. All right. Some common standards used for uncertainty studied include ISO GUM standard, ASME B89.7, blah, blah, blah. These are the decision rules that I talked about. You want to follow these decision rules because if you're in a high-risk market, you don't want to make up your own way to determine if a part's good or bad. You want to follow an industrial standard, and that's that ASME, American Society of Mechanical Engineers standard there. ISO 14253-1 is also another one you could follow. The decision rules, they're going to be relatively close to one another. ISO IEC 17025, it gives general requirements for competence of testing and calibration laboratories. It requires a lot of uncertainty calculations, but as far as how to calculate it, you're probably going to go with the ISO GUM standard. Here's another one, ISO IEC Guide 25, general requirements for the competence of testing and calibration laboratories. Of course, AIAG, MSA, Automotive Industry Action Group, they have a manual on MSA, but it's mostly for gauge R&R studies. Most of you will follow the GUM standard as far as calculating uncertainty goes. And then you'll use one of these for your decision-making rules. So hopefully that helped. If you have any questions, please contact me. Remember, we help you with ASQ certification preparations. These are all the classes we currently offer, and those are the websites. I have a website for each one of those. You can go in there, check out, learn more about the class, and you can also register there as well as paying for the class. All right, keep us in mind for those classes. We'd appreciate it. Thank you, and have a great day. Goodbye.